Okay, in revision 3, we start by looking at the definitions that we need to memorize. The first definition is the definition of magnetic flux. It is the product of magnetic flux density and area normal to the lines of flux. Weber, it is the unit of magnetic flux. It is the flux through a coil of 1 meter squared when placed perpendicular to magnetic field of 1 Tesla. Magnetic flux linkage, it is the product of magnetic flux and the number of turns of the coil. Faraday's law, states that EMF induced is proportional to the rate of exchange of magnetic flux linkage. Lenz's law states that direction of induced EMF is such as to cause effects to oppose the change producing it. Now, let us start the question number 1. Okay, I give you just 1 minute to write. Definition, it's already in front of you, but try to solve part 2. Now, here, just I advise you, the given is the area, but the area in centimeter squared, we have to convert to meter squared. From centimeter squared to meter squared, multiply 10 to the power negative 4. Placed, can you see the word? Placed parallel to the magnetic field. Oh, so what is the value of the magnetic flux? Parallel, it means the angle theta equals 0. And we know that the magnetic flux phi equals BA sine theta. But when theta equals 0, because they said the magnetic flux parallel to the area, so this is the magnetic flux, and this is the area. So when the magnetic flux parallel to the area, so angle theta equals 0, because theta is the angle between the magnetic flux and the area. Then the value sine 0 equals 0, so phi equals 0. Okay? Now, you understand? Okay, guys? Is it clear for you? Okay, now, can you see the second question? Try please to solve with me. Take care, that are very important questions. Question number 2. Think of it. Figure below showed Fleming right hand rule. Okay, so I show you the right hand rule here. Can you see me? Okay. So, okay, my picture is clear for you. So this is Fleming right hand. It's okay, guys? Oh, sorry. I have to open. Yes, now. Okay, so this is Fleming right hand. Current, field, motion. Current, field, motion. It is the same as the left, but what is the difference between the left and the right? In the left, this is current, field, force. Current, field, force. This is the left. Right, current, field, motion. Okay? Yes, question? Yeah. Okay, yes. Okay, thank you. Okay. Okay, now we write the answer here. So the answer in front of us is the current. Okay, and then this is the field, and this is the motion. Now, next question, part B. Read the question, be careful, and try to get the givens. I help you just for the givens. Uniform magnetic field of flux density B is applied perpendicular. So theta equals 90. Theta is the angle between magnetic flux density and area to the plane of a circular conducting loop of 2 turns. So N equals 2. With resistance, so we have R. R equals 0.4 ohms. If the magnitude of the magnetic flux is increased at rate, can you see rate, Weber per second? So this is the rate of change of magnetic flux density. So it is delta B by, oh, no, this is the magnetic flux, not B, phi. It is the magnetic flux, not magnetic flux density. Then it's delta phi direct, so it is given delta phi by delta t, it's Weber per second. So it is 31 multiply 10 to the power -3 Weber per second. Calculate the induced current, so we need I. Of course, first we use Faraday's law to calculate the EMF, and from EMF we calculate the current. Start. Okay, ready? Now let us solve the first part. Faraday's law states that EM delta T. Now, already the given here is delta phi by delta T. So delta phi by delta T is given. N equals 2. So it's 2 multiply delta phi by delta T, multiply 31, multiply 10 power -3. So the answer of this part is 6.2 multiply 10 to the power -2 volt. This is the EMF. We have the resistance, so we can use Ohm's law to get the current. Remember, V, I, R. So we can get I. I equals V. V now is EMF over R. EMF is 6.2 multiply 10 to the power -2 over R, which is 0.4. By using the calculator, the answer will be 0.155 ampere. Okay? Now, next question. Look at this question and try to understand. Okay? Okay, let us think of this. Read the question with me. L-shaped loop. This is L. L letter. Can you see? This is L. That's L. L. Okay. Loop of wire is placed in magnetic field of. So we have B. So B, magnetic flux density, is 0.035 Tesla. as shown in opposite figure. Calculate the total magnetic flux. Here we have two areas. Area number 1 and area number 2. So we calculate the flux through the area number 1 and the flux through the area number 2 and add them up. Flux equals what? Magnetic flux equals B A sine theta. What is theta? Theta is the angle between magnetic flux density and the area. Then we need the angle between the area and the magnetic flux. In area number 1, when we draw right angle, the triangle here, so this is the angle theta. Let this theta denoted by theta 1. So in theta 1, so this is the triangle for theta 1. This is theta 1. This right angle triangle and this angle 25, so we can calculate theta 1, the angle between magnetic flux density and area 1. Theta 1 equals 90 minus 25, so theta 1 equals 65 degrees. Now we can calculate phi 1. Phi 1 is the magnetic flux through the area 1. So we can use that area A1 B sine theta 1. Okay? A1, what is the area here? The area 1 equals the same as the area 2. Equals, it is rectangle each one. The length 35 and the width 20. So it is 35 multiplied by 20. 35 multiplied 20 equals 700 centimeter squared. Convert to meter squared. Okay, so divide by 10 to the power 4, it becomes 0.07 meter squared. From centimeter squared to meter squared. So the area 1 is 0.07 multiply magnetic flux density, which is 0.035 multiply sine theta 1, 60. Okay, by using the calculator, it will be 2.22 or 22 multiply 10 to the power negative 3 Weber. What about phi 2, the magnetic flux through area 2? Let us see here. Of course, this is horizontal, so it's parallel. So this angle is 25. Then this is the angle theta 2. So it's parallel, so alternating angle. So theta 2 is 25 degrees. Okay. Then phi 2 through the second area, it's A2 B sine theta 2. A2 is the same as A1, the same area, 0.07, also be the same, 0.35, sine what? Sine 25. We calculate this value, it will be 1.04 multiply 10 to the power negative 3 Weber. Now, what is the total flux? So the total flux equals the phi 1 plus phi 2. When you add them, it will be 3.26 multiply 10 to the power negative 3 Weber. Okay, guys? Now, next question. Try to solve. Okay. I said write two factors that affected the induced current in the coil. So this is a coil. Okay. When we connected that coil to galvanometer, and if we have a magnet, north and south, and we move the magnet through the coil in or out, Then we have deflection in galvanometer. How can we increase that deflection so we can increase the induced current? We have 4 factors. Number 1, just we need 2 factors, any 2. Magnitude of B, okay? So this is effect, magnitude of magnetic flux density. Magnitude of magnetic flux density. Number 2, the area of the coil. Number 3, number of turns of the wire. Number of turns of the coil or of the wire. Okay. Number 4, rate at which the coil turns in the field. It means the rate of movement of the magnet. So rate at which the coil turns in the field. So that are the 4 factors. You can write any 2, but remember the 4. Now, part B. Now, read it, and then try to write the givens. Yeah. Let us study this. Coil has 80 turns, so N equals 80. And 0.12 meter square cross-section area. So this is the area, 0.12 meter square. It makes angle 67 with magnetic field of flux density. So this is the angle direct between the area and the magnetic flux density. So this is theta. We use sine. So 67.5 degrees. Okay? And they said if the magnetic flux density was increased by, so we have delta B, increased 0.004 Tesla in 1.59 seconds. This is delta T, 1.59 seconds. Calculate the induced EMF. Oh, the induced EMF. Okay. But before to do this, we have to revise how can, change in flux. So note that change in flux happen in 3 different ways. Number 1, change in flux density. Or number 2, change in area. Or number 3, change in angle. So if any change happen in that 3 things, EMF will be induced. Now, we have here a change in what? In magnetic flux density. What is the formula of E induced? It is here. We can draw absolute, we can use absolute value or without, no problem, but it will be positive. So it's N delta phi by delta T. We need the magnitude. Okay? Here, we have here N equals 80. Delta phi, we have a change in B. So we use delta B A sine theta. Delta B, it is 0.004 multiply A 0.12 multiply what? Sine angle. So it is sine 67.5 divided by delta T. Delta T is 1.59. The answer of this is 2.23 multiply 10 to the power -2 volt. Now, next, Okay, read the question, be careful, and then try to solve. Yes, Adam? Yeah, I will check. Yeah.
Mister, to find the
Yeah.
area of a square, you have to add the sides, right?
No, who said that? Let us read. A square loop of wire length, each side. The area of a square, Adam, is side times side. Okay? It is side times
Okay,
side.
thank you, Mister.
No, welcome. Adding the side, it's a perimeter. Side times 4. Very good. Now, a square loop of wire has one turn, so this is N. And each side, so the area equal 0.75 squared. The area is the side length squared. Placed in uniform magnetic field of, this is B, with an angle, this is theta. What is meant by change in magnetic flux linkage? It is the product of magnetic flux and the number of turns of the conductor. Okay? Already, this is given to reduce the time in the definition. Now, part B, calculate the change in magnetic flux linkage. We need delta what? N phi or N delta phi. If the angle between the loop and the magnetic field increased by, okay? Now, here, okay, N delta phi. It's N phi final minus N phi initial. In the initial, the angle theta is 30. Type. In final, what happened? The angle increased by 40. It is not 40. 30 increased by 40. So it is 30 plus 40. So the angle in final theta is 30 plus 40, which is 70 degrees. Take care for that. Look, it has 4 marks. Now, N phi final, you can say it's N B A sine what? Sine 70. This is final. Minus N B A sine 30. Now, what is N? N equals 1. What is B? 0.32. What is the area? 0.75 square. We can take N be a common factor. Then it's 1 multiply 0.32 multiply the area 0.75 square multiply open bracket sine 70 minus sine 30. Yes? Yes? Yes, mister. Is it possible to get the result of the angle 30? No, 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 not 30 minus 40. He said increased, so it's a plus. Okay? He said increased, so it's a plus. Okay? Okay? Can you follow? It's okay? Now we find the answer of this. Then the final answer. Yes? Question? Okay, thank you. Welcome. So the answer here by using your calculator, it will be 0.08. Remember, it's Weber. So this is the change. Okay, guys. Now we go to question number 6. Finish this. Okay. Any question? Okay, guys. Is it clear now for you? Any question? Yeah. Good. Now, go to this question, please. Read the question. Be careful. And here, it said rectangular coil in the following blue has 80 turns. So we have N, the number of turns, 80. So this is N. And the 250 centimeter wide and the 30 centimeter long. So this is 250, this is 250, 225, and this is the long here, it is 30. So this is the, okay, centimeter. Half of its area is located, it's okay. Half is located in magnetic field of value. So this is B, which is directed out of the page, out of the page. Can you see the dot? It means out of the page. The resistance of the coil, this is R. Okay, so what is the required here? If this an AC generator coil, how can you increase the EMF induced? Okay, said stay only 2 ways. Okay, so I said that before, we can do it oral. Coil with more turns N, coil with larger area A, increasing the strength of magnetic field B, increasing the frequency of rotation of the coil. Do you need from me to write, or you can write it? Okay, if you need from me to write, just raise your hand. Okay, or oral? Yes, Adam? Yeah. Yes, Adam. Okay. I will write, it's okay. Now.
Yeah, thank you, Mr.
Yes, welcome. Now, here, to increase the EMF induced, number 1, okay, use coil with more turns, with more turns, N, we increase the number of turns. Number 2, coil with a larger area, coil with a larger cross-section area, A. Number 3, increasing the strength of magnetic field, increasing the strength of magnetic field B. Number 4, increasing the frequency of rotation, move it faster, increasing the frequency of rotation of the coil, or you can say move the coil faster. Now, part B, find the magnitude of induced current. So we need I induced. If the coil is moved with a speed 2 meters per second downwards, oh yeah. Now, let us think of this. So it moves downwards here. Can you see? This is the velocity. So this is 25 centimeter moves downwards. Let us withdraw here. So this is the wide. It's a 25 centimeter. So when we change 2 meters divided by 100, 0.25 meters. It moves down with velocity 2 meters per second. So at the beginning, okay, can you see? At the beginning, there is no area. It is just the wire. So the area at the beginning is 0. When it moves down 2 meters per second, it means it moves 2 meters, okay? 2 meters in what? In 1 second. So this is the movement. So here, we have area. So delta A now formed. This is delta A. So what is delta A? It is the length multiply width, because this is area formed. So it is 0.25 multiplied by 2, which is 0.5 meters squared. That happened in what? In 1 second, 2 meters per second. So delta T equals 1 second. Okay, now, what is B? B is given here. B equals 1.4 Tesla. So B equals 1.4 Tesla. Okay, he said here 80 turns. So N equals 80. Now we use EMF induced. So EMF induced equals what? N delta phi by delta T. The change in flux now happened because it changed in area. So it's N B delta A by delta T. Sometimes we say, okay, I prefer this way. N equals 80. Multiply B, 1.4. Delta A, 0.5. Delta T is 1. Then the answer is 56 volt. But we need the current. Then we use Ohm's law. Okay, because we have the resistance. The resistance is given in the question. It said the resistance is 24. So we can get the induced current. So the induced current equals V over R. V is the EMF over R. R is 56 and EMF is 56 and R is 24. Calculate this. It will be 2.33 ampere. Okay, guys? Yes, question? Yes, but Mr. The area of rectangle is 25 multiplied 30. Yeah, but this is not the whole area inside, because they said just this side moves down, not all the area. It is a part of the area outside. It's okay? And they said 2 meters per second. Just we use here in 1 second what will happen. Okay? Yes. Now, next question. Yes, question? Yeah. Okay, thank you. Now, question number 7. This is about Lenz's law. Now, think of it, please. Lenz's law is very important. You have to understand it. Be careful. Okay? You understand? It's very important. Yeah. Before to solve this question, we have to revise Lenz's law. Look, my friend. Lenz's law states that if we have a magnet, north, south, just remember this figure that I will draw. Now, we have here permanent magnet. The permanent magnet has permanent field. So the permanent field, because the magnet, it's from north to south. This is permanent north. When the magnet, okay, move towards the coil, okay, into the coil, what will happen? Before the magnet, okay, go inside the coil, when the magnet just move toward the coil, EMF induced in the coil produces the current induced. This current makes the coil act as a magnet. So now here, this is the direction of the current induced. Okay? Now, coil or solenoid has a current, then it will be magnet. Then we have here electromagnet. It is temporary magnet. So this is north, will be ripple. Now, when the coil go into the coil. Now, what happened if the magnet moves away. So this is N and this is S. Okay, and this is, of course, the coil here, moving away. Also, EMF. Then Lenz's law related to the movement. If we have a change in flux, movement, EMF induced in the coil, but in opposite direction of the first case. Then we will get a current, but in opposite the first case. Then what happened? This is the north, according to right-hand grip. So this is the south. But the permanent magnet has permanent field. So always this north attractive. It's okay? Now, let us we see that question. Read it and try to answer alone. He said, the opposite diagram shows loop of wire placed in perpendicular magnetic field. Suddenly, the magnitude of the magnetic field begins to increase. So we have a change in magnetic field. Describe the effect of the magnetic field on the loop. Yes? Question? Mister? Will it happen the same with south? Yes, yes, the same with south. Yes, yes, Yahya. If we change the south, it will be the same. Yeah. Now, tell me please what happened. Okay. Do you remember right hand grip? Okay, follow me please. Right hand grip. Okay. So the fingers represent what? The current, and the thumb represented the north. Can you see here B? B, it is out of the page. Is it? Then we have a current induced. When B changed, we have current induced inside the field. Okay? So what happened here? So because B changed, follow me to this piece. Here, we have here current induced in the field. According to right-hand grip, the direction of current is anti-clockwise. Can you see? So this is the direction of current. This current, I1, okay, in the field, because what? Because it changed in magnetic flux density. But according to Lenz's law, induced current in the loop is opposite to that change causes it. Then we have here the current I2 in the loop. So I2 is opposite to I1. According to what? According to Lenz's law. To Lenz's law. Do you understand? So the direction, so EMF induced in the loop, okay, in clockwise. Okay? So we write here, field in loop will be opposed to given B. That is into the page. So inside the loop, here we have B into the page, okay? Producing a current, okay, clockwise in the loop. Do you understand, guys? Okay, yes, question. Please ask me if you don't understand, because everything must be clear. Question number 7. Oh, yes, again, question number 7. First here, we have a change. I said, suddenly, the magnitude of magnetic field increases. then what will happen? Around the loop, we have induced current here, around with the green one. So this is the current induced because the change in flux. According to Lenz's law, induced current in the loop in opposite to I1. I1 because here, I1 here, because what? Because right hand grip. The direction of current is here anti-clockwise. But in the loop, magnetic flux, okay, density will be produced into the page opposite to producing it. The given magnetic flux density is out of the page. So, according to Lenz's law, can you see here the figure? According to the polarity here is opposite to the given is out of the page, so producing inside the loop into the page. And this magnetic flux density into the page produces current. This current will be clockwise. Okay, I hope you understand this. Okay, now, next. Okay, try to solve question number part. Yes, still question? Yeah, welcome. Now, question part number 8, also according to Lenz's law. Try to solve it. Okay, ready? Okay, now, he said the diagram below shows moving magnetic, okay, magnetic bar. So this is the bar magnet and the solenoid. If the bars are moved to right, so the movement in this direction. Determine the poles of solenoid at A and B. Now, when the bar magnet go into the coil, so this is the north. According to Lenz's law, the polarity at A is opposite. He said it do not enter, so it will be north. The same as this, repeat it. Then at A, it will be north. Now, if the magnet leave it out, this is north. Then at B said, no, do not leave, it will be south, attracted. So it is south. This according to Lenz's law. Okay. Now, let us solve another question. Yeah. Next. Try to solve this question, please. 2 minutes to solve. Also, this according to Lenz's law. Okay, ready? Okay, let us explain this. I said the opposite diagram shows magnetic bar. This is the magnetic bar attached to suspended spring over a solenoid. If the bar is pulled downwards to height H1 level, so it will be pulled down and released. Now it will be moved up. So it will be, okay, moves up. So the movement is up. When the magnet leaves H1, according to Lenz's law, this is north. Then when it moves out, the polarity here, it will be south. to attract it. Then the polarity down is north, okay? Now, this north, it means what here? This is the north. Then, according to right-hand grip, okay? So this is the north here, okay? Yeah, no, this is the north, it's okay? Here. So this is the direction of the current produced. Because this polarity is north. Why north? Because the back at H1 is south. Why south? Because the magnet moving up, away from the solenoid. Now we have here the current. Then the current moves from what? From Y to X. So the direction of the current is from Y to X. Explain. That's what I explained, but I write it for you. When the magnet get to level H1 and induced, okay, and induced current, okay, and induced the current is producing because of a changing in magnetic flux. Okay, guys? Okay? Do you understand this question, please? Yeah. Now, just, we take a break for prayer and I'll come back. Okay, now we go to question number 10. Look at question number 10. He said the opposite figure shows a square conducting loop. Moves at constant speed. Take care. Constant speed. So the speed is constant. Through a uniform magnetic field until it's totally out of the field. So start at this point and end at this point. Okay? Now, state Faraday's law, this is already, I gave you at the beginning of the lesson. But now, in part B, he said, on the blue coordinate axis, draw the graph of magnetic flux through the loop versus distance x. Okay, so what will happen? The magnetic flux depends on what? It's B, A, sine theta. Because it's perpendicular, so depends on B, A, and angle. But now here, the area, B is constant, it's uniform. And the angle is 90. Then phi depends on the area, okay? So phi proportional to the area, the change in area. At the beginning, the area is 0. So phi is 0. So this is at the beginning, at 0. When that square moves with constant velocity, then phi increases with constant rate, Then it will be a straight line, increases with positive slope. Okay? Until, okay, completely enter the field. So here, this is L increases L until here. So this is L when we finish. This is the first part. When the square completely inside the field, the flux it will be constant. So at this position here, until what? Until here, 3L. So until 3L, it will be constant. The flux, okay, the magnetic flux, it will be constant until 3L. And then the square starts to leave the magnetic field. Then the magnetic flux, decreases gradually, decreases because it depends on the area until to be 0 when completely out. So this is the graph. This is the maximum phi. This is phi maximum. Now, why it is a straight line? Because the velocity is constant. The movement with constant velocity. So phi increases with constant rate. So phi increases with constant rate. Constant rate. Okay? Now, if we write here from, for example, this is O, A, B, C. Now we need to study this graph. So from O to A, what will happen? Note that from O to A, EMF induced. Is it correct? Because we have a change in flux. So EMF induced. With constant value, because phi increases with constant rate, with constant value. Constant value. What about from A to B? No change in flux. It will be constant. Then EMF equals 0. Now, what will happen from B to C? EMF reduced? No, EMF also constant rate. So EMF induced with constant rate, but in opposite direction of the first. So in that one, EMF, in that one, EMF in opposite direction to the first one. This is E1, this is E2, opposite to E1. Now, if he said, draw EMF induced. So if he said, draw EMF induced, take care. With time, how can we do this? We do this? Look, please. We need to draw the EMF induced. Now, this is the time. Okay, guys? And this is EMF induced. Okay? From 0 to the time here, the time from O to A. I talk about O to A. So this is the time from O to A. EMF is constant and it's maximum here. So this is EMF. Okay? Now, from the time, the next time, it's the time of what? Of from A to B. So the time from A to B, no EMF induced. The EMF induced is 0. So here, this is the EMF induced. The last thing, from B to C. So this is the time from B to C. EMF induced, but in opposite direction. So it's down here. Okay? You understand the graph? This is the graph of EMF induced of that figure. Yes, question? Yes. EMF, here it is not the slope. The slope of this line is the change in flux. Okay, here, the change in flux, the slope. It is the change in flux related to the displacement. So take care, my friend. Take care. We need to understand that. Now, here, the slope of this line equals the delta phi by delta x. The change with the time, with the x, with the movement. But here, it's EMF with the time, related to the time in that question. Because here, take care, a lot of questions will come in the exam according to that, according to question number 10. So take care. How can you draw BT? How can you draw phi t? How can you draw EMF t? Take care. We need to understand. And also I give you more questions about this issue. Okay? Now, let us we go to the next question. Yeah. Now, read that question, be careful, and try to solve it. We said the figure below shows square conducting loop of side length L entering uniform magnetic field of magnetic flux density B with constant velocity. Okay, so it moves with constant velocity. Figure 2 below shows the graph of magnetic flux, okay, through the loop versus with distance x. Look, it is approximately the same question as before. Here, phi multiply 10 power negative 7. Now, what about this 3? 3 is the maximum flux. 3 multiply 10 power negative 7. Again, this 3, can you see this 3? It is the maximum flux. Okay? Now what will happen? From 0 to 0.2, oh, this is the length of the side. Because here L, when the square entering the magnetic flux density, the flux increases according to the side, because I said phi proportional to the area, and the area depends on the side, L. Then phi proportional to L squared. Now, 0.2 is what? It is the length of the side. So this is when the square entering L from 0 to 0.2. So the length of the side of the square L equals 0.2, the unit is meter. We need the area. So the area equals the side square. It is 0.2 square, which is 0.04 meter square. Okay, this is part A. Now, follow me. Many questions about this. Calculate the magnetic flux density. How can we calculate this? We know that phi equals B times A. So the magnetic flux density is phi divided by A. What is phi? Phi is given in the graph. The maximum phi is 3 multiply 10 power negative 7 divided by the area that we got it before, 0.04. So the answer is 7.5 multiply 10 to the power negative 6 Tesla. Okay, guys? Next question. If the time of entering the loop completely into the field is 0.1, this is the change in time. Calculate the maximum EMF. The maximum EMF, it is N delta phi by delta T. Okay, now, what is delta phi here by delta T? Here, N delta phi. Delta phi here, the maximum value of phi, or the change, it is 7.5. Okay, so here, now delta phi, here it is 3 multiply 10 power negative 7 divided by delta T, it is 0.1. So the answer is 3 multiply 10 to the power negative 6 volt. Now the important question, try to think of that question with me. Sketch the graph EMF induced and induced and time, where it takes 0.4 seconds from entering and leaving the field. Now, try to think of this. We need to sketch or to draw the graph of EMF induced. Yes? Question? EMF. N equals 1, yes. Now, so what happened from 0 to 0.1? Because it is a line here, so the slope is constant. Then EMF is constant. It's constant value, has maximum value, by the way. That we got it. But in this case, when it's horizontal, no change in flux. So EMF equals 0. And now, when the square leaves the magnetic flux, what will happen? EMF induced in the opposite direction. It is the same value, but in opposite. The maximum value is 3 times the 10 to the power negative 6. 1, you can say 2, 3. So let this point is 3. 3 multiply 10 power negative 6. 1, 2, 3. This point is negative 3 multiply 10 power negative 6. Of course, this is in voltage. From 0 to 0.1, the maximum EMF induced here. Maximum. And then from 0.1 to 0.3, the square already inside the magnetic flux density. So no change in flux. So EMF induced is 0. So in this part, from 0.1 to 0.3. Now starting to leave, then we have a change in flux. Then EMF induced, it will be maximum, but in opposite direction. Now, okay, guys? This question is very important. Take care. Okay, guys? I hope you understand this. Try to think of this question again. You have already the PDF file. Try to solve again and then look at the answer. Next question. We have many, many questions about this because it's very important topic. Now, look at this question, guys. Okay? Now, just I reduce it. Look at question number 12 and think of it. Ready? Because the time. Okay. A single turn circular loop. Single, it means n equals 1. So single, it means n equals 1. Is placed in uniform magnetic field, perpendicular, theta equals 1. To its plane. The magnetic flux density through the loop versus with time as shown. He said if the highest induced EMF is 0.03, calculate the area of the loop. What is EMF induced? Okay, let us we think of EMF induced. EMF induced equals N delta B, because we have a change in B, multiply A over delta T. Follow me, please. Delta B by delta B by delta T. Who is that? Delta B by delta T. From this figure, it is the slope. So we can write EMF equals N multiplies the slope, multiply the area. But we need maximum. So the maximum, because it said highest, E maximum, equals N multiply the maximum slope, multiply A. Now, here, the slope in this part is 0. So EMF equals 0. Now we have two lines. This one, the first one, and this one, the second one. Which one has higher slope? Which one more steeper? Of course, 2, the second one. So the second one is more steeper than the first one. More steeper, okay, than the first one. Then our slope is this part here. For example, if we write O, A, B, C, so we find the slope of BC. Now, what is the slope of BC? Why we use BC? Because it is more steeper than OA. So the slope of BC, which is steeper, okay, equals what? Equals y2 minus y1 over x2 minus x1. Oh, can you see here? All the vertical change over horizontal change. The horizontal change from 25 to 30, it means it's 5, but multiply 10. Then the slope of the line BC equals, but the slope is negative. Okay, take care. The slope of the first one is positive slope, but in this one, it's a negative slope. So it's a negative. The vertical change, which is 0.04, over the horizontal change, which is 5, multiply 10 power negative 6. Okay, we calculate this by using calculator. So fraction 0.04 divided by 5 multiply 10 to the power negative 3 equal 8. So it's a negative 8. The slope is negative 8. Now we go to the EMF induced. Faraday's law said that EMF induced, it's magnitude of N delta phi by delta T. Okay, now we said delta phi by delta T is the slope. So it is absolute value of N multiply the slope, multiply the area. He said, find the area. EMF induced is 0.03. N is 1. We take the absolute value here. Absolute value of negative 8 is 8. Multiply 8. So we can get the area. So the area equals 0.03 divided by 8. The answer is 3.75 multiplied by 10 to the power negative 3 meters squared. Do you understand this question, guys? Okay. Yes, Adham? Yes.
Mr.
Yes.
In the graph, oh, never mind, sorry.
Okay, no problem, no. Okay, another question. Take care. We have many questions about this because this part has higher marks in the exam, and it will be the difficult part in the exam. Lenz and Faraday. So try to concentrate with me in this lesson. Now, next question. Question number 13. Try to solve it alone. Yes? Yes, Mr. Y. We take second slope because it's more steeper. Find the slope of the first. Okay. Find the slope of the first. What is the slope of the first one? Okay, let us resolve here. What is the slope? It is the vertical change 0.04 over the horizontal change, which is 15 multiply 10 to the power negative 3. Calculate this slope. Okay, fraction 0.04 divided by 15 multiply 10 to the power negative 3. The answer is 2.67. Look, but the slope of the other one is 8. So it's more steeper. Why we take 8? Because it said the highest. If it said lowest, we take the first one. But lowest is 0. Okay? The EMF, the minimum value is 0 in that question. Okay? So this is, I answered. Is it? Now, next question. Think of that. He said calculate the induced EMF during the time interval CE. So EMF induced, he said. We have here the phi and the time. So what is EMF? It is N delta phi by delta T. This is Faraday's law. N equals 1. Okay? A single, because it said a single. So N equals 1. Then E equals delta phi by delta T. Delta phi, it means initial flux minus, okay, final minus initial. Now, Phi at C, phi at C is the initial, okay? Is the initial flux. What is the value of phi at C? It is 10 Weber from the graph. Phi at E is the final. What is the value? It's -5 Weber. Now, what is the change in flux? Delta phi equals the phi final minus, okay, minus what? Minus phi initial. So it's -5 minus 10, it's -15 Weber. EMF, it's, okay, magnitude of N delta phi by delta T. So it's magnitude of 1 multiply -15. What about delta T? Delta T, it is the time at E minus the time at C, which is 0.6. The time at E, it is 0.6, minus the time at C, which is 0.3. Then the difference in time is 0.3 seconds. Then the change in second is 0.3. When you do this by the calculator, it becomes -50. Okay, we take the absolute value, magnitude, it's 50 volt. Okay, guys, I hope you understand this question. Next question. Okay, now read the question. State Faraday, it's okay. We stated it before, we don't need to repeat. Now, find the magnetic flux through the coil at T equals 0. Now, read the question with me to write the given. Okay, guys, now, here. Okay, here. A coil, it means N equals 1. Of area, so this is the area. It is 0.4 meter square. Has, a coil, sorry, has 300 turns, so N not equal 1. N equal the 300. And a resistance, so this is R, 25 ohms, is placed in magnetic field that varies with time as shown in the figure. This is B and this is T. The variation of the magnetic field of the coil with time is shown in figure A. Now we have figure A and figure. Now, he said find the magnetic flux when T equals 0. When T equals 0, the magnetic flux density is 0.6. So B equals 0.6 Tesla. And the area is 0.4 meter squared. Magnetic flux phi equals B times A. So the magnetic flux phi equals BA. Just we do substitution. B equals 0.6 multiply A 0.4 equals 0.24 Weber. Now, in the first 2 seconds, the magnetic field is decreasing as shown in the graph in figure B. Answer the following. Now, what is the direction of induced current clockwise during the period? Now the ring is settled inside the field, no movement. Then what is the direction? The direction of the current, induced current, by using right-hand grip. Yes, Adham? Yes. Yes, Adham?
Sorry, by accident.
No problem. Yeah, so here, can you see, use your right-hand grip? It is into the page, okay? Can you see, please? Okay, it's into the page. Okay, guys, now can you see here? Because it's into the page. So this thumb represents the field. Cross, it means into the page. And this is the direction of the current. So it's what here? It's clockwise. Okay? So the direction is clockwise. So this is the direction of the field in the ring. Why we don't say opposite? Because he said no movement. So this is direct the current in the field because the field. So now the direction here is clockwise. Now, next question. Find EMF induced. We talk about what? From 0 to 2. We need EMF from 0 to 2. Now, what is B initial? B initial equals 0.6. What is B final? B final from the graph is 0. What is the time? So delta T, the change in time, is 2 seconds. Now, change in flux density, delta B, equals B final, which is 0, okay, minus B initial, 0.6, equals negative 0.6 Tesla. Now, what is EMF induced? N, okay, of course, the magnitude of N, delta phi by delta T. So it's N delta B A over delta T. N is given in the question, which is 300. Multiply change in flux is negative 0.6. Multiply the area, 0.4 over delta T, which is 2. The answer of this, when we take the magnitude, would be 36 volts. He said the magnitude of the current. Oh, it's easy. We use Ohm's law. So remember, V equals I times R. We need I. So it's V over what? Over R. E is 36 and R is given 25. So the answer is 1.44 ampere. Next question. Yeah, think of that question, guys. In that lesson, in that revision, we will cover, inshallah, all the ideas about induction. Read the question, be careful, and try to understand. He said, two conducting rods, M and N. So this is M, and this is N, okay? This is N, and this is M. Lie in a uniform magnetic field, this is B. A third conducting rod O, so this is O here, it's okay? That O. Slides on them, then we have a movement of O at a constant velocity. Then at the beginning, okay, the area here, can you see? The area increases with constant rate. So we have a change in area. Okay, now calculate the magnetic flux. Okay, he said he said slide on them from the point A, to the point B at 3 seconds with constant velocity. Calculate the magnetic flux. Phi equals what? Equals B times A. What is A? It is area of triangle. So A equals the half base times the height. It's area of triangle. The base is 0.6 and the height 0.3 from the figure. So it's a half multiply 0.6 multiply 0.3. Okay, we calculate this. Half multiply 0.6 multiply 0.3. The answer is, okay, 0.09 meter squared. This is the area. What about phi? Phi equals B times A. B is given, which is 0.0 0.35. Area that we calculated 0.09. So the area multiply 0.35. The answer is 3.15 times 10 to the power negative 2. 3.15 times 10 to the power negative 2. Remember, the unit is vector. Find EMF induced after 3 seconds. Oh, EMF induced equals what? It is one coil, but we write the formula. It's N, okay, delta phi by delta T. Here, we have a change in area. Okay, so we can write here N, okay, B delta A by delta T. N equals 1. B is constant, 0.35. Delta A that happened, delta A is 0.09 over delta T over 3. Then the answer here is 1.05 multiplied by 10 to the power negative 2 volt. Next question. Okay, he said the state length law. We stated at the beginning of the lesson. We don't need to write again. But now just think of part B. Take care. Part B according to Lenz's law. Think of it. Yeah, try. I give you 2 minutes to solve. Now, let us reanalyze the question. Take care. Okay. Now, set the figure opposite two conducting loops are facing each other. They are face to face. An observer see along the axis of the loop. So this is the observer. What is the direction of induced current in the smaller loop? If it moves with a constant speed towards a larger, then the smaller moves towards here. Can you see? So this loop, the smaller one, moving towards. Now, first of all, here we have a current, okay? Clockwise current. In the bigger loop, we have clockwise current. This is the current in the loop. By using right-hand grip, then we have magnetic field in the bigger one. This is the magnetic field in the bigger one. Can you see? It's north. Right-hand grip. Because the smaller moves towards, then the magnetic field in the smaller loop, the same, north, Lenz's law. Now, this is north. Then we have induced the current in the smaller. By using right-hand grip, the direction of what? The direction of the current in the smaller, because this is right-hand grip. So it's counterclockwise, anti-clockwise. Okay? So this question about Lenz's law, it's very important question. Now, next. Define, we don't need definition now. Let us think of this question. Right, think with me of that. He said, the figure opposite shows two identical bar magnets, A and B, drops from the same height through two conducting rings. Which magnet will pass through the ring faster? Is also about Lenz's law. What is the difference between the two rings? You know that? Is there any difference between the two rings? Can you see that gap? We have here gap. It's okay? Or break. Is it? Now let us analyze. When the first magnet drop, here we have north. Is it? So this is north. It's okay? North, north. Then according to Lenz's law, in the ring A, we have north, according to Lenz's law. North, north, then we have a current in the ring A. So this is the current. Then it will be repel the magnet A. This is A. Now, what happened to the magnet B? Now, here, it go in this direction. Yes, but what happened here? This is also north. But because this gap, the current cannot be completed. Because this gap will be stop the current. Then no EMF induced. So the north cannot be completed. Then there is no magnet in the open ring. Then the magnet B moves faster because nothing will happen in the ring because it's open. Then the answer here will say it is B. Why? Because ring A, this is the reason, okay? Ring A will induce current I in it, producing magnetic, okay, field, magnetic field opposite. But ring B has break, so no the current induced. But ring B, because it has break, so no current induced. You understand the trick of that question? It has 2 marks or 3 marks in the exam. Now, question number 18. Try to think with me. Question number 18. A rectangular single turn loop, N equals 1, moves at constant velocity, perpendicular, theta equals 9, uniform magnetic field. The figure below shows the graph of variation of magnetic flux through the coil from the time it enters the field until it leaves the field completely. Now let us analyze. At the top, when it's straight, so no change in flux. No change in flux. Okay. Here we have constant change in flux, constant change in flux. So EMF induced is constant value. Also this one, EMF, constant, but in opposite to the first case. Also the same slope, so the same value. Now we answer. Part A, I said, at which time interval then this EMF is 0? What is the interval? From 5 to what? To 15. So the EMF, because no change in flux. The area equals, calculate the magnitude of magnetic flux, B. Now, which formula we use it? It's easy. Phi equals B times A. So we can get B. B equals phi over A. What is phi? Phi is given in the graph. So B equals phi, which is 4, over the area, 2 times the 10 power negative 2. The answer becomes 2 times the 10 power 4. Remember the unit Tesla. Next question. Now, try to think of that question. Okay, I give you 2 times to analyze the figure. I give you 2 minutes. Ready, guys? Let us we think together. Okay, I read the question with you. A coil of wire situated in a uniform magnetic field of flux density B. The coil has diameter. Oh, this is the diameter. So we can get the radius. The radius is half the diameter. So it's a half multiply 3.6. It is in centimeter. We convert to 2 meter. So it's a half multiply 3.6 times the 10 power negative 2 to be in meter. And then we can get the area. The area is by r squared because they said coil. Okay? Then by calculation, we can get the area. So the area now is 1.02 multiplied by 10 to the power negative 3 meter squared. I said consists of 350 turns, so this is n. The variation with time t is given. Okay. Now, show that for the time t equals 0 to time 0.2 in this time interval, okay, can you see? The electromotive force is 0.08 volt. What is EMF? EMF, it's N delta B A by delta T. Why I said that? Because the given is the change in flux with time. So delta B over delta T is the slope. So it's N multiply the slope, multiply the area. Now we need to get the slope. The slope from 0 to 0.2. Now, when you draw this, you will get it at the middle. That is 45. Then the vertical change is 45 millitesla over the horizontal change. Now, we find the slope. So the slope in this interval equals 45 multiply 10 power negative 3 because it's millitesla divided by the horizontal change is 0.2. We calculate this. Fraction 45 multiply 10 to the power negative 3 divided by 0.2. The answer is, okay, 0.225. Okay, Tesla per second. Now, EMF equals N. N is given. N is 350. Multiply the slope, 225. Multiply the area that we got it before. This 1.02 multiply 10 power negative 6. Now, this multiply by 350 multiply by 1.02 multiply by 10 to the power negative 3 equal, yes, it is 0.08 approximately volt. Then we finish this part. Next part, he said, on the axis of the following figure, show the variation with time of the induced EMF from t equals 0 to t equals 8. Oh, now, this is number 1, the graph, and this is number 2, and this is number 3. In number 2, EMF equals 0, no change. But what about the slope in 1? Because EMF depends on the slope. Now, in case of 3, the slope 3 equal the vertical change, which is 45 times 10 to the power negative 3 over the horizontal change. What is the horizontal change? It is 0.4. Oh, it means the slope 3 equals a half slope 1. It means EMF induced in that one, so we can say this is E3, and this is E1, and this is E2. So E3, its value is half E1. E1 was 0.08. half multiply 0.08 is 0.04 volt. Now we need to draw sketch. Okay, now first from 0 to 0.2 the value of EMF induced is 0.08 here. So this is 0.08. From 0.2 to 0.4 EMF is 0. So this one 0.2 to 0.4 it is 0. Next, from 0.4 to 0.8 it is 0.04 in opposite. Then it's here at middle. It's okay. So it's here at the middle exactly. So this one here is negative 0.0. Okay, guys, do you understand now? Now we cover the most of ideas. Let us solve again question number 20, another one. Solenoid of diameter 6 centimeter. From diameter, sorry, maybe we take more than 2 hours today because it's a big topic. Diameter equals 6 centimeter. So the radius equals 3 centimeter. 3 multiply 10 power negative 2 to be in meter. He said solenoid, so we can get the area. It's by r squared. Yes, question? Yes. 19 part B, yes. Again, part B, he said, look at the figure. In the first one, EMF E1, we calculated it is 0.08. From 0.2 to 0.4, EMF equals 0 because it's horizontal. From 0.4 to 0.8, it's negative slope. And in the first part, from 0 to 0.2, it is steeper, more than from 0.4 to 0.8. The slope in the third line is half the slope of the first line. So EMF in the third line is 0.04, half 0.08. But it is in opposite, in the negative. So from 0 to 0.2, EMF is 0.08. From 0.2 to 0.4, EMF is 0. From 0.4 to 0.8, it's a negative 0.04 volt. Next. Now, okay, here we need, okay, he said the meter equals 6. So we can get the area. So the area equals 2.83 multiply 10 to the power negative 3 meters. This is it. He said for 540 turns, so this is N. In uniform magnetic field, the variation with time of magnetic flux density, this is B. So this is B and T. He said calculate the maximum induced electromotive force. Now, okay, follow me. Here we have EMF. Here we have EMF. Here we have EMF. But in this one, EMF equals 0 because no change in flux density. We have E1 and E2. He said maximum. Which line is steeper than the other? E3, is it? This one. So we need to calculate the slope. But first of all, we talk about EMF. EMF equals what? N A delta B, because we have a change in B, by delta T. Delta B over delta T, it is the slope. So the maximum EMF depends on the maximum slope. So we need the slope of this line because it's more steep. The slope equals what? The vertical change 250, but it's in millitesla. So 250 multiply 10 power negative 3 over the horizontal. The horizontal, this one, can you see here? Each one is 2. So this part, the horizontal one, it's from 6 to 7.2. So it's 1.2. So over 1.2. Then the maximum EMF, so EMF maximum equals N, which is 540, multiply the area, 2.83, multiply 10 to the power -3, okay? Multiply the slope, which is 250, multiply 10 power -3 over 1.2. When you calculate this, it will be 0.32 volt. Now we go to the multiple choice question. The easy question, I solve it quickly, and the hard, I explain. Now, think with me in question number 21. The magnetic flux in Weber through, okay, placed parallel. Parallel, it means the magnetic flux is 0. So the answer is because parallel, theta equals 0. Now, circular coil, he said, okay, what is the angle between the magnetic field lines and the normal? Take care. So this is B, this is our theta, and this is A, but we need the angle between the magnetic flux density and the normal. We calculate theta. How? Phi equals dA sine theta. From the given, you get theta equals 46.7. By the way, this is easy question because if I doing exam like this, I have to put this as one of the answers. But because it is not answered, so it is wrong. But actually, in multiple choice, we put this as one answer, but it is not the required. We need the other one. The other one, okay, the theta between B and the normal, we say it's 90 minus this angle. So the answer will be approximately 85. Take care for this question. Now, in this one, can you see here? This is a positive according to this, according to this. Then this is the north. So also, this is the north according to what? Lenz's law. Then this is the direction. Okay? Then this is the direction of the current. So the correct answer here is this. Yes? Yes, question? Yes. Yes. Mister, how did we know 46.7? Oh my God. Just we find from the given, my friend, here. I solved it. It's okay. Because the time, just the time. He said, okay, phi is that one. 1 multiply 10 power -4 equals the B, this one, 0.625 multiply the area. This is the area. Oh, this is the radius. It's pi multiply r squared, 2.5 times the 10 power -2 multiply sine theta. From this, you calculate sine theta, and from sine theta, shift to sine the answer, you can get theta. Okay? Next. Now, can you see that one? Okay. He said this is the bar. Okay, bar magnet hanging between two identical coils as shown. What would happen to the bar magnet? This is the current. Can you see here? So this is the north. And also, okay, what happened here? This is the north. So this is the south. So is the bar magnet stationary? North attracted to the south and south attracted to the north? No. Because one tricky here. Can you see? 1, 2, 3, 4. This magnet has 4 turns. But the other one has just 3 turns. So this, the first magnet to the right is stronger than the left. Then it will be moved towards E. You understand the trick of this question? If the number of turns is the same, it will be at rest, stay at rest. Now, next one. This is a tricky question. Follow me, please. This is important question. Okay, he said the figure opposite shows 2 identical wires carrying the same current. One of them is connected to, okay, here. What will happen to the magnet when the current passing through the wires and two. Can you see here the wire? They are in opposite direction. Then they will repel each other. Then we have here a force of repulsion. Can you see? This is the force. Then this rod will be moved in this direction with velocity. Now, velocity, movement, Fleming left hand, Fleming right hand rule. Now use your Fleming right hand, current. No, we replace, okay, here. Okay, Fleming right, can you see? Current, field, motion. So, okay, the movement to the right, and the field is out of the page. Then the current is down. Then here, the current here, direction is down. Then this is the direction of the current induced. Now, this is the direction of the current. Then this becomes north. And the magnet is south, will be attracted. Then it moves down. Look at this. It contains many roots. Okay, right hand grip. Okay, and also the relation between the two wires. This question actually is very nice question, and it's important. Okay, next question. Okay, this is easy question and direct. Just I give you the answer because we solved the question harder than it. Now, this also one also it's easy, increases. Okay, now look at this question. Now, what do you notice about this? He said the graph, follow me please, because this is important question. The graph below shows magnetic, okay, flux density versus time for a coil with a fixed area placed perpendicular to magnetic. Now, what will happen here? Here we have a change in magnetic flux density. And this change is constant change. So this is constant change. Then EMF induced is constant. It's constant. It's okay? So it is a straight line. And also here, but here no change. So EMF equals 0. Here also we have a change. EMF is constant. But here, EMF depends on the slope. The first one is steeper than the second one. So the EMF in 1 is greater than the EMF in 2. Then this is wrong, this is wrong. Now, one of the last two one is correct, the first one, because EMF induced in the first is more than the second because it is steeper. Then the correct answer is. Now, next. The diagram opposite shows loop of wire in uniform magnetic field. How much the loop moves to have a changing in flux? Actually, if it's rotate right or left, no change. Up and down, no change. But if it will be rotate around the axis, we have a change in what? In angle. So only change this one. But the other one, no change. Nothing happened. So EMF induced just when it's rotated around the axis. Next one. This is about Lenz's law. Okay, here, this is the current. So this is north, this is north. It's okay. It's okay. So because this north, it will be moving here. And also the same, this is north, this is south. So it's moving away. Then the correct answer of this one is the last one. Now, this one is easy question. You can solve it. It's direct. Okay. And also this one, he said, in the figure opposite shows a coil fixed on a magnet suspended in the spring. The magnet and the coil oscillates up and down together. Oh, so no change in flux because no change. Okay, change in flux if one of them is fixed. Here, he said will not induced. So when moving the loop, direction parallel. Parallel, it means no change. Now, next. This one, look please at this here. He said a student conducts an experiment by oscillating aluminum ring vertically between the 2 points. Okay, now the ring at A minimum EMF induced. At C is maximum EMF induced. At B, it's away, minimum. Okay? So a string, okay, fixed the midway. Which of the following graph shows the magnet? Then it will be oscillates from minimum to maximum to minimum. So this is wrong. We said from minimum to maximum because from A to B to C. Then this is also wrong. This is also wrong. Only this is the correct. Last one. Last one, we're using Fleming right hand or right hand grip. Okay, Fleming right hand. Now, look please at this. I said the figure in a circle loop shows which one has clockwise. Okay, of course, number 1 wrong, no change. Number 3, no current. Now we have 2 and 3. Look, guys, please. This is, okay, in the field, we have movement. Follow me, please. In the field, it's out of the page. Then we have the current produced in the field clockwise. According to Lenz's law, the current in the loop 2, it will be opposite. Then clockwise, it's loop 2. What will happen to loop 4? Now, according to Lenz's law, when it will leave, the current, it will be reverse. So it will be anti-clockwise. Then the correct answer is 2 for clockwise. The correct answer will be 4 for anti-clockwise. Okay, guys, I hope you understand this lesson. Okay? Now. Okay. Okay, guys. Any question? I stopped the recording. Any question? Yes. Yes, Ma'mun.
Excuse me, Mr. Could you please repeat question 11?
Okay, question number 11.